Hi, my name is Ankai, and this summer I worked in the Robbins lab. And first, some background about my research. In commercial agriculture, over-fertilization is a huge problem, and it causes nitrogen runoff, which can lead to algae blooms, as we can see in Ithaca. This is happening in Cayuga Lake. And we have a new promising solution in the form of sentinel plants, which turn purple under low nitrogen stress. And with these sentinel plants, we think that farmers can fertilize their crops with more precision. However, these plants most likely do not yield as much as the commercial varieties. So the objective of my research is to find the optimal density and distribution of sentinels for creating a reliable nitrogen field map. So here are the methods I used. First, we use spatial effects data from drone images. And then from these drone images, we can create maps such as these with NDVI, which is a vegetation index that measures how well a plant is growing. And we're using NDVI as a proxy for nitrogen level measured in the field. And then after we have these maps, we can perform ordinary Kriging interpolation, which is a geostatistical technique that predicts values at unmeasured locations based on values at measured locations. And Kriging is better understood with a visual. So here we have our spatial map of NDVI. These are the true nitrogen values. And then we sample 15% of these plots. We sample 15% of these true nitrogen values here. And then once we have this sample, we can put this into the Kriging algorithm to produce this prediction heat map, which we then compare to the true nitrogen values to see how accurate it is. And we see that at 15%, you can get the most significant areas of nitrogen deficiency and abundance. However, this is just one example of a distribution and one example of a map. So we ran an iterative Kriging process. So we repeated this process 900 times, each with a different map and different random distribution. And we plotted two quality metrics, R squared and Kriging failure rate, which are defined here. And the benchmarks we use is we want our R squared to be above 0.5, so above this red line. And we want our Kriging failure rate to be below 5%, which is below this red line. And we found that 15% is an ideal sentinel density, considering that the sentinel may have some measurement error, which I'll talk about here. So in this example above, we assume that the sentinel is a perfect reporter. So it can capture 100% with 100% accuracy how much nitrogen is in the field. However, in the real world, this is most likely not possible. So this is the actual nitrogen values. This is an example of a perfect reporter. And then we added 15% measurement error here. And we see that the area of nitrogen deficiency has shifted a little bit according to this prediction, but it's still relatively accurate. But once we get to 30%, it becomes completely inaccurate. And then we also tested planting these sentinels in a strip distribution, so planting them in rows. These were the results. For the strips, the average R squared is shown by this bar in the middle of these box plots, and compared to the mean R squared for the random, denoted by this red circle. And we see that the red circle outperforms the strips, so random distribution is more optimal. So key takeaways, number one, 15% is a good optimal density for sentinels, and random distribution is more effective than strip distribution. And big picture conclusion, sentinels can potentially reduce over-fertilization and nitrogen runoff. And in the future, we'd like to determine sentinel yield and accuracy, as well as how financially viable they are, and if the spatial pattern strength affects the amount of sentinels we need to plant. Thank you very much.